So, my name is Vladimir. I work for Lyft, as was mentioned, applying deep learning computer vision to the problem of building HD maps for self-driving. Today, I'm not talking on behalf of Lyft, and this means that I will not talk about self-driving, and I will talk about some other topic. I have some experience in machine learning competitions, and if we'll have time at the end of this talk, I'll talk about some applications of image augmentations to different types of the challenges, what winners did there. So why I'm talking about image augmentations today? As many of you, people have hobbies in their free time. As a nerdy guy, I have a nerdy hobby. So I participate in the development of the open source library for image augmentations, and a couple of weeks ago, it became part of the PyTorch ecosystem, and because of this, I get a couple of talks, like in Adobe, at work, and somewhere there, and I decided that it's a good idea also today to talk about image augmentations, about the technique, what it is, why do we need this, and some applications and corner cases, okay? So, image augmentations. Let's talk about computer vision tasks. What do we have? We have image as an input. As an output, we need to give some kind of meta information. It can be some kind of label, and in this example, human, sheep, or dog, or it may be more spatially accurate information like bounding boxes around different types of the classes, or it may be even more spatially accurate information. You give per pixel label, what class it is, and this corresponds to semantic or instance segmentation. So kind of straightforward. Of course, there are a lot of different tasks in computer vision. Array is booming. If you come to CVPR or some other computer vision conference, you will be amazed by how many interesting and creative ways the research community came to just to deal with the images. But these are the most mature. So if we are talking to some company and you question what guys do you use in production to map data into money, it will be most likely classification, less likely detection, but still these three algorithms allow big companies and small startups to map data into money and just basically widely used. Okay, so need for label data. As many of you know, it's experiment some kind of evidence, more label training data you have, better your algorithms are. It's not general statements and it's not very linear. You see on the right side of the slide some kind of logarithmic scale for mean average precision. I believe it's on the, I don't remember the data set. Link. Later on, I'll share the slides, so you can click on this link and just check it out. So more data you have, you take exactly the same model, exactly the same pipeline, you do everything exactly the same, you add more data, and accuracy of the models goes up. And this is how people improve accuracy of the model. Overall, there are two ways to improve model. One of them is engineering part. You basically get more label data. Another is scientific. Let's have more fancy network, better pipelines, optimizers, activation functions, some other shady magic, and that's what scientists do. But it's less reliable. You can't ask scientists in your company, how much time will it take you to improve our model twice by Friday? And he will say I don't know, it's very unpredictable. So people add more label data. Especially in this world that we are entering right now, where deep learning is trying to propagate. It's already widely used for computer vision. Right now, in the last 2 years, with the recent advancements in research, it gets to NLP, and tabular data is also catching up. Deep learning become a thing, and due to the large capacity of the models, deep learning benefits the most out of a lot of label data. So label data is good, and if you have some problems to solve and you want to improve the accuracy, label your data, and it may work. The issue is getting labeled data is tricky. You need to collect this data. You basically need to have some kind of either operators or have some pipelines, so just something should happen there. Then some types of the data is expensive to collect and difficult to label. Good example of this is medical imaging. If I look at some image and it's I need to distinguish dog versus cat, I can do it. Everyone can do it. It's dog and this is cat. But if we are talking about some X-ray scan and you need to say, there's pneumonia here, I have no clue how to distinguish this. So you need for this data labor, not some kind of cheap person in I don't know, Russia or someone else, but some kind of expensive doctor in the United States, and the cost of your data labeling becomes pretty big. And much worse than this, if you look again at many medical imaging data sets, you can see that 5 doctors give slightly different label to this data set, and you still, again, need somehow to deal with this. Basically, getting a lot of label data in medical imaging is tricky. Next one, privacy and legal issues. Again, coming back to the medical imaging, let's say if you talk about United States, you talk about healthcare, you talk about medical imaging, you talk about building some tools for second opinion or showing on the images some kind of like nodals or something like this. Technology is here. Unlike many other domains, technology for this is already here, and some students can, it's basically student work to develop train some UNet or something else for segmentation work. The issue is, but at the same time, we don't see this explosion overall like on the market. Why? Because FDA doesn't approve. It's very harsh to get approval. And again, privacy and legal issues. In this sense, I believe many of you, or those who work in this medical imaging domain, you work with a data set, large data set of 200 images. I remember use case when I trained a model and there was no any more data, like only 50 images. So basically getting data there was tricky, and you kind of like need to survive and with a small amount. So what do you do? There is like technique called image augmentations. So in this example, I tried to depict what it essentially does. You have some kind of data, and it's the easiest way to do this with images, and then you apply some kind of transformations that make sense, and they don't move this image away from the original data distribution, and this is a way to enrich, to increase the size of your data set. Still, adding new different data is better than applying augmentations, but augmentations is a very powerful technique. So in this example, some original parrot, horizontal flip, crop, medium blur, contrast, HCV, shift, gamma, something else. Okay, so why do you need augmentations? As I just mentioned, size of the data is important, and it's a way to increase size of the training data set. Example, you have some kind of like images, you have like size of, 1 million images, then you flip them all horizontally, and then you get 2 million images. Not exactly like this, but kind of, so it's the way to do it. And if you add rotations and crops and everything else, it's just better. You can make networks invariant to the perturbations of the input. Let's say you have some kind of like image and you want your network to be robust to the same image but with small rotations or some kind of shifts. You want some kind of regularizer. You want your network to be fine with these small or maybe big types of the perturbations, and you can do it with this. Maybe again, when I'll cover examples, I'll talk about some applications of this. Okay, more scientific way to think, and way that I typically think about this. When you talk about neural networks, you pass job interview or you pass exam in university, and you ask what type of regularization you know. Typically you say L1, L2, dropout, batch norm, maybe something else, early stopping. And augmentations is also regularizer, and I like it the most because if you talk about L1 or L2, it's just some number that you choose on cross-validation. With the image augmentations, you have some kind of interpretation of what's happening. You take an image, you look at them, you look at the transformations that the augmentations create, and this intuition and domain knowledge that you have allow you to improve your network performance. So regularization, it's like my favorite interpretation. First three are equivalent, it's just basically slightly different way to think about it. 4, this is kind of production use case. So when you take some class or maybe work on some kind of like benchmark data set like ImageNet or something like this, what you typically do, you take 20% of this data set, you train on this like 80%, you evaluate on this 20, you say that's how my model performs, life is good, and then reality, and it's good to publish a paper or maybe win a competition or something like this. But then reality comes. So what do we have? Okay, I promised not to talk about self-driving, but let me mention it. So let's say you do some kind of self-driving company, and you collected a lot of data during summer, and it was like daylight, life is good. You collected this data, you labeled this data set, then you trained your model, and right now, this is end of the November. And your cars are driving in the evenings. And what does it mean? And you apply these models, and they don't perform as well as that was happening on this like Sunday, like light, like nice, bright images. The reason for this, distribution changed. Your train and test changed. It's one example. Another example, and I've seen some papers about this, when you talk about satellite imagery, you train your networks, I don't know, for segmenting roads or buildings on the images from Toronto or New York or Las Vegas, and then you try to apply this to some cities in China, and you see significant accuracy drop. And what do you do in this situation? The way to do it, so what happens? You train on some images from Toronto, you apply on some images from China, and you let's say, on the images from Toronto, you cut off 20% data set, you validate on this carefully, and this performance on your validation in Toronto is not related to your performance in China. Why? Because distributions are different. What do you do in this sense? Not that much, but you try to regularize your network more. And the way to do it, what typically I and many other people do, you basically apply a lot of augmentations, and it gives you some confidence that your networks will be more robust in the different types of the domain. Again, good example like medical imaging, when you have trained set collected in some hospitals in one country using some type of the hardware long ago, and then you build your own startup, you're coming to some other hospital and trying to sell, okay, guys, I have a great algorithm because it has some kind of score and some other blah, 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 and they tell you, okay, let's apply this to our images, to this our apparatus, this has different resolution, and everything just sucks. I mean, it's like my friends has this actual experience, and again, way to deal with this, augmentations. Doesn't solve problem completely, but you have more chances for getting a deal with this hospital, with your startup that you're building. Okay, augmentations to add accuracy. Augmentations to regularizers, so here's some kind of research result that I really like. So in this second column, it's some accuracy on the image net with the standard type of the augmentations, crops, horizontal flips, color jitter, and you get some type of the numbers. And on the third and fourth, some kind of more advanced augmentations that people choose using reinforcement learning, some shady magic there. But what's my point of this? You get exactly the same data set, exactly the same network, you apply better augmentations, and you get better accuracy. So you didn't spend time or money on labeling more data, but you get better model. Why? Because better regularization. It's one example. Second one, and this is what was happening in that paper. Authors use reinforcement learning to apply different set of the transforms. They try to choose them. Basically, it's a grid search in the space of the image augmentations, but with some twist of reinforcement learning, spending enormous amount of GPU time, but still pretty impressive work. Next one. Another thing that you may talk about this, again, active area of the research. You have some kind of models, and they're accurate, and life is great, but you need to get this same quality model to some kind of embedded devices that has some limitations in terms of your compute, I don't know, like web camera or something or maybe, again, self-driving or something else. And what do? You want accurate model, but it's just, too heavy. So what can you do? You can apply augmentations, and if you do it properly, life may work. So in the second row, it is light network with strong augmentations, and in the third row, it is big network without strong augmentations. And as you can see in the last column, the accuracy on the validation set of ImageNet is almost exactly the same, and this is the way to go. So basically, again, same story about extending your data set, getting accuracy. Okay, this is again coming to this question about different training data set. I love this paper, came, I believe, in the June of this year. So what people were doing, they took some kind of trained object detectors, some standard trained on Coca, and they applied, okay, sure, it may be not a bird, it's a dragon, but more or less, I can see why the network confused, and so they found a person like Jon Snow, I believe, and then they twisted brightness and then something else, and your network is not working anymore. Why? Because your test distribution is different from your train, and on these plots above, you can see how fast and how drastically this performance of your network fails. So again, from the claim, I trained this net model on this benchmark data set, Coca, ImageNet, OpenImages, something like this, and now it will show the same performance in my production system that works in completely different data distribution. It's a powerful statement, and to prevent from this, try to use strong regularization. Again, augmentation is a good reason. For example, if people train this network and used more aggressive brightness switches, probably second image will go well, yeah? So, and this is another example of this, so kind of similar to the previous slide. So people, what did they took some kind of well-trained state-of-the-art object detectors. It's page in the MM detection repo, and it's blue column shows the original performance, and then they show their performance on the corrupted data that was affected by different types of the perturbations. Data that we as a human still understand, but kind of network messed up. It's not exactly as adversarial attacks. For adversarial attacks, you need to switch some pixels, do some kind of complex involved stuff. Here, some simple transformations, and your network starts failing. Okay, how augmentation process happens? We are talking about computer vision. You have some images on the disk or in memory or somewhere else. Okay, on the disk. You have, 1,200 different CPU threads. Each thread independently reads an image, applies random augmentations, then all of them collapsed into the batch, and then you add this batch, feed to GPU, forward pass, backward pass, updating network, weights, things like this. Life is good, and people were happy because you want to optimize your GPU time when you're computing, because GPU instance on AWS costs $23 per hour, and CPU instance significantly less. So you're trying, your GPU is your bottleneck. So what I try to say, so that's how it works, and it's important that your augmentations are fast enough, because if your augmentation is slow, CPU part will become a bottleneck, and you will inefficiently use your GPU resources. It is expensive for you, expensive for the company, so you want fast image augmentation library, image augmentation pipeline. Okay, what image augmentations are? Some examples. I showed like before this some picture of the parrot and a couple augmentations applied to this, and here more aggressive examples. On the left again, same parrot with 12 different transforms, and on the bottom some example of this. You can be very creative of this as a human. You can apply some kind of blur, you can shift channel in the image, you can like drop some parts of the image, you can apply something else. On the top right, there are some images I did this just for fun. It's my home city, St. Petersburg, and it was like some weekend, and I will work on self-driving, and people at work said something about bad weather, and just, okay, let's do this thing. Let's add some kind of augmentations to this library that I'm like building that will randomly apply kind of imitation, mimic some rain and fog and maybe like sun to the images. I'm not sure how natural it looks. I'm not sure how much can it help, but still kind of like cool types of transform, and you can be like, much more creative with this. Okay, augmentations with guns. This is pretty cool area, and I know at least few startups that raise decent amount of money that claim that we build like new synthetic data that will allow you to, do some breakthroughs in your area. And what do? They take some kind of image, they use some kind of another reference image, and they do style transfer. So on the left column, original image, in the middle, image that kind of defines style of your resulting, and on the right, what happens after you apply it. Looks pretty natural, life is good, and again, active area of research and making money out of synthetic data. Next one, again, spatial transforms. What happens with spatial transforms? As I said, like the most widely used image augmentations in the computer vision pipelines in the world is horizontal flip. Why? Because, you look at some dog, cat, or parrot, you flip it, still dog, pet, or carrot, label is the same, it looks natural, life is good. If you work with satellite imagery, some top view imagery, you can do like any types of rotations, flips, crops, transpose, scaling in reasonable limits. It still makes sense, and it's the way to increase data set. If you look at recent or maybe computer vision competitions in the domain of satellite imagery, all of these transforms, like in this image, are used. Why? Because if you want to get top results, if you want to beat state of the art, you need to use different top techniques, and image augmentations is a must-have in your vocabulary of techniques as a computer vision engineer or data scientist. Again, at the bottom, some examples. You also should have, when you work with the key points, and this area is also growing, especially in the domain of face recognition. I didn't want to put for the image anyone's face. I believe this fox looks pretty cute. So it's this. And on the right, also kind of interesting transforms I try to emphasize here, especially this elastic transform. If you talk about some natural images and you try to do this weird elastic transform that I had on the right, it just doesn't look natural. But for medical imaging, works really well, amazingly well. Because why? Because if you do some kind of slice, there are some cells and they're moving around, and you do this elastic transforms. For my eyes, still some cells moving around. Doesn't make it strange. So again, elastic transform, pretty good in medical imaging. And again, examples at the bottom, and try to emphasize, you can be very creative with these augmentations, hundreds of them. Okay, so tricky part. The reason why my collaborators and I started developing this library that I'm using at work, in Lyft for our self-driving, and also people use in other big companies and machine learning competitions and in academia and things like this, is because we're doing a lot of bugs. You write some computer vision pipeline, and you want, with some probability, some interesting transformations to be applied to images, bounding boxes, masks, and you don't want to mess up any indices. You don't want to flip one of them and not flip other. And this was a pain because, software engineering is still essential part of the machine learning pipelines. And pain that you get there, you try to mitigate, you try to solve it. And this was our motivation to build this library. Okay, so now I will try to go through some examples. In many ways, way that, let's say, people, okay, let's say I'm at work or I have some other pet project or something like this, and I want to figure out what is the state of the art, where should I read, what should be my next implementation, next experiment in this domain. One way to do it is look at the recent papers, but all recent papers claim we are not like everyone else, we are state of the art, and you get hundreds of these papers, and all of them claim exactly the same. And it's pretty hard to distinguish what is real, what is not, and just how to deal with this. Another source that works better for me, original what I do. So if I have some task, I look for computer vision competition that was trying to solve similar problem. Why? Because you have some kind of benchmark. This data set presumably is closer to what you do. You look at the winning solutions. They have not just one trick. They have plenty of them. And what is important, so when you're in academia, and especially, let's say when you establish professor, you can do cool stuff because you do. But if you're grad students, your goal is like to publish good papers at the conferences, and research in many ways is secondary, not for all people, but for most of them. And in the sense, people tend to lie in the papers or skip some important details and things like this. Still, most of the knowledge comes from the papers, but competitions, leaderboard, as people say, leaderboard will not lie. So in this example, challenge was input, image, top view, and you need to identify buildings, all pixels belonging to buildings. And my friend Alexander Buslaev, who's also collaborator on this library, he got first place, he got 50K in prizes, and I wish I also participated in this because problem looks relatively straightforward. And as I mentioned for top view imagery, natural transformations will be a while, like rotation, still you rotate this image, makes sense. Rotations, flips, scaling, optical distortion for whatever reason worked here, and HCV shift, slight shift in the colors. He used this, a bit of shady magic here or there, some tweaks to neural networks, some optimization training pipeline, and got 50K, and he spent on this about 4 days. Okay, next problem, similar top quarter, space net road extraction. Again, Alexander Buslaev, semantic segmentation. What's the goal? You get some kind of imagery, and you need to detect roads. If you look at OpenStreetMap in the United States, I mean, all roads are here. Canada, I don't know, didn't check, but the situation is good. But if you're talking some rural areas in Asia, or maybe in Russia, or even in some regions in Europe, many roads, especially small roads, they are missing. And there is no easy way to find them, and another way just to do it, you just take satellite imagery, you do some kind of detection, you try to find this road network, some kind of verification may happen there. Okay, 5 minutes left. Let me do one more slide, and then you'll ask your question. So anyway, road extraction, challenge, this type of flip, transpose, shift, scale, arcade, HCV shift. Okay, this was a good one. On this problem, we spent 10 days. Prize money was 12,000, we split this. This was sad. So at the time, library wasn't happening, and we used horizontal flip. Again, for this car, as you can see, it makes sense, flip. Some kind of rotation, some scaling, switches and brightness, and some shifts in HCV shift. What was cool from this paper, just for fun? And I did this competition for fun, just an easy problem, let's do it, and surprisingly we got to the top. And then after this, just for fun, I decided, okay, let's write a paper, I preprint and put this on archive that describes this network that I used. And I put this there, and guys, I had more than 100 citations, and it's cited more than all my physics work that I did in grad school in 5 years. Okay, so I was out of time. So what we have here is another transformation. This was a good one because train and test dataset were really different, and for authors, just to make your network more robust, and this distinguished them from other participants, they applied how many? 30 different transformations you can see at the bottom. It's just number of huge, yeah? Okay, something else, some transforms, some out of time, life is good. Some other examples, segmentation, medical imaging, first place out of 1,500, good result. Another result. Okay, thank you.
Great talk, Vladimir. Can you show me what is the PyTorch library that you're talking about?
I'll tell you. So it's called Albumentations, and probably ping me later. I'll give you links. So I should probably add this to slide. My mistake. I can tell you later. Okay.
Great talk. I was wondering if you ever considered that over time, with the volume of augmented data that you're adding to your data set, whether your models are actually learning the augmentations as opposed to the subject matter, if the proportion of augmentations overwhelms the original.
So the answer is I don't care. The reason for this is how you work with the data. You have test data set that represents target distribution that you have. And this test set should be as accurate as possible with respect to what you really want in your life to measure. You also choose your metric with respect to what you actually want to measure, and then your train set can be complete garbage. It doesn't matter. I mean, of course, if it's a good, clean, nice data set, you get better models. But realistically, you don't care about this. What you try to optimize, your model performance on the test set. And if applying extensive augmentations improves your model on the test set, life is good. If it doesn't, life is bad. And this is the way that you deal with this, whatever network remembers, yeah.
So for applications like self-driving that you're aware of, the test set is the real life. and when its life is bad, it's pretty bad.
This is a good example, but no, like I'm talking about model performance. Let's say I'm training some object detector for, self-driving, yeah? We have extensive, like very accurate data set that covers presumably all corner cases, and if we like find during disengagement something else, we extend it. So our test set is like very big thing, and we care about this like test set for this detection task a lot. So in this sense, we are pretty sure that network that performs on this test data set is what we really want.
Thank you very much for your great work. I have a question. So when you are working on the image augmentation, how do you think if I crop those objects you want to detect or classify to different kind of backgrounds? So let's say I want to detect or classify a cat, and I crop this cat, or I crop all the cats in my original data set, and I find a different kind of background. I put this patch on different background. Do you think it's a good idea for augmentation?
This may work. I've seen one example when it works, but this is kind of related to the previous question. So I remember I was working on some problem where you needed to distinguish some kind of classifier. We need to distinguish not like what is depicted on the image, but what type of the camera was used to do it. So basically you take exactly the same image. Let's say I take a picture of you like from this point with Android and iPhone, and then I need like network takes as an input this image and say who's Android, who's iPhone. Network that we did develop that problem had 98% accuracy, meaning network can distinguish this underlying structure, like really low level features that your post-processing or like camera matrix creates really well. And what does it mean? It means that if you take your cats, crop it from one image that was taken presumably most likely with one type of the camera, you put this to the other type of the camera, it may happen that your network will not understand and think this is about good image augmentations, but this is will react not to the actual object, but to the fact that color distributions or underlying small features in this cropped cat and its background are slightly different. I do have example when it works, and maybe if you apply some kind of post-processing, smooth blurring techniques or try to mess up this type of distribution in such a nice way, it may work. But if I had similar problem, I would probably go with a bit different solution. Basically, it may work, and cross-validation will say who is right, who is not, but looks slightly sketchy.
Thank you very much for the talk. So I have two questions. One is, do you recommend Gaussian blur as a kind of a augmentation to replicate the motion blur on videos? Number one. Number two, so when it comes to, say, transient data set, like videos in general that is a function of time, is there any architecture that learns from the previous movement to predict the next movement kind of thing, or no?
Answer to the second question is yes, there is such a work that tries to predict previous movement from second movement, sure. In terms of its answer to the second question. Answer to the first question, if you have images in which motion blur happens naturally, let's say camera or driving or things like this, of course it's better if you just basically collect this data set that has this type of the feature. But there are transformations like median blur, you can go Gaussian blur or median blur, and you can apply them. They look similar but not exactly the same. They may work, and if they work, life is good, check it with the cross-validation score. All this deep learning is in some senses alchemy. Of course, you develop some kind of intuition and you can say kind of insights and you try to understand what's happening, but in practice, it's still a lot of alchemy, it's still intuition, and it's still cross-validation score will tell you who is right and who is not.